Okay, so diode is referred as a unidirectional device. Unidirectional device. Now, unidirectional would mean current in one direction only. Okay, and similarly, let's move towards the diagram. What does it look like? So, a diode looks like this. The electric symbol for the diode will look like this. Now, this terminal is known as the positive and this is the negative one. Now, why is this unidirectional? Because it only allows the current to flow in one direction only. Now let's try to connect this in such a way in which circuit that we can observe its behavior. Let's say we connect it in this way or in this manner as the starting point. Let's say this is our bulb, and let's connect the same diode but in reverse this time around. This is the only component in physics which actually does affect, or you can say the outcome is affected by the way it is connected in the circuit. And this symbol is for a bulb. We are using a bulb for visual indication that whether it is switched on or not. This is the positive terminal of the battery, this is the negative, positive and negative. Now, if I try to track the path of current, that would be in such a way that the current leaves the positive terminal. Now, it tries to go through the diode. Now, we are just checking this right now. It's not confirmed that the current will actually flow, but right now we're just checking it. So if my predicted direction of the arrow of the current is similar to the direction of the diode, what am I or how am I going to see that? Look at the pointing side of the diode. The diode is pointing towards the right side in this diagram. So the current it's going to allow will also be in this direction. This is just a way to remember this, right? This is not a scientific method to look at. This is just one way to remember this, that's all. So if the direction of the current that you have figured out is similar to the direction of the pointing side of the diode, then the diode will allow this current to flow. So this current will be allowed to flow through the battery, and the circuit will effectively look like this to you, that the diode was probably not a part of the circuit at all. It means that the resistance of the diode is approximately zero when it is conducting, when it does get a favorable condition. And what is the favorable condition? That the current that the battery tries to inject into the diode is in the same direction in which the diode is connected. It is still there, but it's not going to resist. It's not going to take any energy away from the circuit. Now, this is what it simplifies to. This is what it, if I just say that, this is what it simplifies to, that it looks like, it feels like the diode was not a part of the circuit to begin with because it has so less resistance if the conditions are favorable. Now, let's move on to the second diagram. Over here, we see that the battery still tries to cause the flow of current in this direction. But in this diagram, we see that the current the battery wants to inject, that direction of the current is opposite to the direction of the diode, what it is expecting. So under these circumstances, the diode will not allow the flow of current and will become so resistive that it would look like that the circuit is completely blocked. And that is represented as infinite resistance. And how to represent infinite resistance? By an open circuit. Open circuit would mean that there is no way any current can flow through it. It doesn't mean the diode physically has been removed from the circuit. No, it's still there. But it behaves in such a way that we can equally depict that, or you can say equally represent it in such a way that it is so highly resistive in this condition that no current will be allowed to flow. And it is so highly conductive in the first case that it will instantly allow the flow of current through it. These are just simplifications to understand it. And there are specific names for both of these conditions. The first one, in which the resistance averagely, or you can say effectively, becomes zero. This condition is known as forward biased. We will call this forward bias situation, in which the diode has been given its favorable voltage, or the voltage it was expecting, or the voltage at which it switches on. In that condition, we will call this forward bias. So whoever hears forward bias would understand that the direction of the current and the direction of the diode are same. So the current is allowed to flow through it. On the other hand, if we move towards this side of the circuit, this will be known as reverse biased. That the diode is connected in such a way that whatever direction of the current is trying to flow through now was not allowed to flow in the first place. Now, in this diagram, you may notice that we have only switched, or you can say we have only swapped the places of the diode. First, it was connected in this way, now it is connected in this way. What if the diode is still in place, but we change the level of the battery, or we change the terminals of the battery? Let's try to explore that, and then I'll go back to the questions and ask you if there's still a problem. Now, in this case, when the current is allowed, the bulb will appear to be on. The bulb will be on. In this case, the bulb will appear to be off, which gave us the idea that the diode is a unidirectional, or it is only going to allow the current in one direction, but not in the other one. It does allow the flow of current in one direction, which is the forward bias condition, whatever that may be for that circuit, but it fails to convert, or fails to allow the flow of current in the reverse bias condition. Let's move on to another example. This time around, I'm not going to swap the position of the diode. I'm going to make sure the diode stays connected in this configuration, but I will swap the terminals of the battery only for the interest of science. That is it dependent on the diode, or can the supply also introduce this problem? So if you'll notice, what I've done in this case is I've introduced the battery to be in the opposite direction over here. So first is a control case in which we can see that everything is in the favorable or the best situation possible. Positive terminal on the upper side, negative on the lower side, and this is the direction of the current the battery wants to inject. So our expected direction of the current and the direction of the diode are in the similar, or are in the same direction. Again, this is just a trick to remember. This is not a scientific method. We will see that the diode has become forward biased, and it is so light on the circuit, or you can say it is so that its resistance appears to be zero. So even if I do draw this in the circuit, it has no participation in the circuit, right? Do you understand this idea? All right. So in this case, it will look something like this, that the diode is not a part of the circuit and the bulb will be on, right? On the other hand, we will look at this. Now, try to visualize this problem. Now, the positive terminal is the lower end and the negatives on the top. Again, I tell my students just to check whether the current will flow or not. So they sometimes visualize it in the incorrect way. They think that the current did flow in this case, it does flow in this case, it does flow in this case, and when it reaches at this point, the current stops moving because the direction of the current is opposite to the direction of the diode. No, this is just a testing way. This current that I've drawn with the blue color will not flow in the first place. We are just testing it. What will be the direction of the current when it does reach the diode? Otherwise, if you're so intelligent, or if you can figure it out just by looking at it, then fine, don't draw these arrows, because the current will not flow, because this is a reverse bias condition. So what the battery wants, or is trying to do, is that the current flows in this way. But when we try to match this direction with the diode, it's in the opposite way. So this looks like a reverse bias condition. This looks like a reverse bias condition. And under these circumstances, we see that the diode is infinitely resistive. Its resistance is so high that the current is not being allowed to flow. So the battery stays on the same side or the same orientation, but we miss out the diode in the first place just to represent mathematically or in terms of diagram that it is so highly resistive now that it is as good as a broken circuit. Only this behavior is depicted when the circuit is broken. So if with voltage, with a resistor, and with the diode component, if the current is not flowing, that means that the diode is so highly resistive that it's not allowing the flow of current at all. So in this condition, the diode or the bulb appears to be off. So I'm going to take a pause at this point.